Hello everyone, welcome to CAIE Science, and today we will be solving the remaining part of the October November 2022 for 4209. In the first part, I think we just did 5 questions, okay? And now we will start from question number 6. So let's begin. Question number 6. An aqueous solution of cobalt 2 chloride is a pink color due to the presence of this complex ion. Okay. About the table 6.1 to describe what is observed when the named reagent is added to the aqueous solution of cobalt 2 chloride. Okay. So when this NaOH is added, these water molecules are substituted by OH molecules. Okay, and the color of this cobalt product will be blue. This complex of cobalt has a color of pink. You have to remember these colors. Okay, there is no other way to explain this. You just have to remember the colors of this complex. In your syllabus, you are required to remember the colors of complexes of cobalt and complexes of copper. Okay. So this complex of cobalt has a color of pink, and when it reacts with NaOH, it forms a complex which has a color of blue, which forms a blue PPT. So its state will be in solid state. Okay, and then when an excess of HCl is added, so what will be the color? The color will be blue, but this will be a blue solution. Okay, or you can write it as aqueous. Okay, now write an equation for the reaction between this complex of cobalt and NaOH. So when this complex of cobalt reacts with NaOH, the H plus ions, OH, hydroxide ions, they react actually to form, uh, sorry, this complex. Two of the water molecules are substituted with OH molecules. Okay, and the overall charge becomes zero. Okay, because OH is negative and there are two OH molecules, and the oxidation state of cobalt is 2 plus. So 2 minus and 2 plus cancel out to give the charge of 0, and then you have 2 moles of water. Okay, so this is your equation. You have to balance the equation as well. Okay, now write an equation for the reaction between cobalt and an excess of HCl. Concentrated HCl. So when this cobalt complex of cobalt reacts with Cl ions, chloride ions, it forms cobalt Cl4. This complex forms. Okay, and this complex is a charge of 2 minus, because there are 4 chloride ions and each chloride ion has a charge of 1 minus, and the charge on cobalt is 2 plus. Okay, and you have 6 moles of water. Okay, so these are your two complexes. This complex has a color of blue, and this complex also has a color of blue. Okay, but this is a blue solid and this is a blue solution. Okay, now define the stability constant. So what is the KSP? It's actually KSB, stability constant. K stable, K stability. Okay, so it's the equilibrium constant. The equilibrium constant for the formation for the formation of a complex ion in a solvent from its constituents. Okay, from its constituent ions at equilibrium. Okay, so this is your full definition of the K stability. Okay, now write an expression for the K stability for this cobalt complex. So how this cobalt complex will form? Um, this cobalt complex will actually form when this initial mole of cobalt, uh, which is in aqueous water, this cobalt, this complex of cobalt, when this complex of cobalt reacts with ammonia, excess of ammonia, so this complex will form. Okay, this complex plus X plus H2. So now you have to write the K stability constant expression for the K stability of this complex. So in the K stability, we don't include water molecules because water is acting as a reagent, oh sorry, as a solvent. So we will not write the concentration of water in the K stability. So actually the K stability is concentration of products divided by concentration of reactants. So what is the product here? It's actually this complex ion. So concentration of this complex of cobalt divided by, you have the concentration of initial 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 complex of cobalt and concentration of ammonia as well, and you will have a power of 6 on ammonia because there are 6 moles of ammonia. Okay, so this is your K stability constant expression for this K stability constant. Now give the units for the K stability of this complex. So for the units, uh, these concentrations are in mole per dm cube. So this mole per dm cube, this mole per dm cube cancel out with this mole per dm cube. So you will have a mole minus 6 and dm cube 18. Okay, so this is your these are your units, dm cube 18. Okay, the numerical value of the K stability of this cobalt complex ion is this. Okay, in an aqueous solution, the concentration of this complex of cobalt is 0.074 mole per dm cube, and the concentration of ammonia is 0.48 mole per dm cube at equilibrium. Calculate the concentration of this complex. Calculate the concentration of this complex ion. Okay, so you are given the expression, K stability expression in the part 2. Okay, and you are also given, you are given the value of K stability and the concentration of this complex and this ammonia. You have to find the concentration of this, only this complex. Okay, so let's do it. You are given 3 values and you have to find only one value. So K stability is 7.7 into 10 to the power 4 is equals to, you are given the concentration of complex 0.074. Okay, and now you have to find the concentration of this complex ion. Okay, and you are also given the concentration of ammonia, which is 0.48. power 6. So from here you will calculate the concentration of this complex, which will be 7.86 into 10 raised to power minus 5. Okay, this is your final answer. Now moving towards next question, question number 7. Question number 7. The structural and displayed formulae of three aromatic compounds A, B, and C are shown in figure 7.1. Okay. Compare the relative acidities of these A, B, and C. So which one is most acidic? The acidic one will be an acidic will have an acid group. So this carboxylic group is an carboxylic acid group is an acid. But which of them will be more acidic? So it will be C, because in C you can see there is another electronegative group, which is chlorine. So it will try to attract electrons to itself. So OH ion will more weaken. Okay, so C is the most acidic. Then you have A, and lastly you have B, because in B you have no carboxylic group. You have an alcohol group, or you can say phenyl group, which is not as acidic as this carboxylic group. Okay, now explanation. So chlorine and carbonyl group are electronegative groups, and this causes greatest weakening of OH ion. Okay, this causes a greatest weakening of OH ion in C. Okay, then you have A. So carbonyl group in A is electronegative. Okay, electronegative. So causes weakening of OH ion. Okay, so this is your reason. Now moving towards next part B. Methyl benzene can be made from benzene by an electrophilic substitution reaction. Okay, identify a compound that reacts with benzene to form a methyl benzene. So this is the methyl benzene, and to make methyl benzene from benzene, you react it with an halogenoalkane, and here you have this methyl benzene. So the compound must be CH3Cl or CH3Br. You can use that as well, but CH3Cl is an ideal choice. Okay, so chloromethane, and the catalyst which is used is AlCl3, or you can say aluminum chloride. Okay, aluminum chloride. Now the first step in this reaction is the generation of this electrophile, CH3 plus electrophile. Write an equation for the reaction that generates this electrophile. So firstly, this chloromethane reacts with AlCl3 to form this electrophile, CH3 plus AlCl4 Cl4 minus. Okay, so this is your first equation. Then this electrophile is attracted by this benzene ring. Okay, describe the mechanism for the reaction between benzene and CH3 plus electrophile include our relevant curly arrows and charges. So this pi bond ring is electronegative. Oh, sorry, has a charge density, so it will attract this uh, incoming electrophile. Okay, then what will happen? This electrophile will attach to the ring. Okay, like this, or like this. Okay, and then this hydrogen will donate its electron to ring, and it will form H plus ions. Okay, so you will be here, you will have this methyl benzene plus H plus ion. Okay, so this is your mechanism. You have to remember these mechanisms. Identify a suitable reagent to oxidize methyl benzene to benzoic acid. Okay, so the conditions are alkaline KMnO4. Write an equation for this reaction using O to represent one atom of oxygen from the oxidizing agent. So the reagent is actually hot alkaline KMnO4. Hot alkaline KMnO4, or you can say potassium magnet 7 KMnO4. Okay, and the equation for this reaction is C6H5 methyl benzene CH3. So this methyl benzene reacts with O, the oxidizing agent, which is KMnO4, from this cis benzoic acid and water. Okay, now you have to balance the O. There are three O's. So this is your balanced equation. Okay, now moving towards next part. Methyl benzene and benzoic acid are both nitrated with a mixture of concentrated nitric acid and sulfuric acid to give a mononitrated products. The structural formulae of these products are these respectively. Draw the structure of these two products. So let's first draw the methyl benzene. This is methyl benzene, and then you have benzoic acid. So this is a benzoic acid. Okay, so now you have to attach the nitro group, but where this nitro group will be attached in both of these. So you have to see which of them is a 2,4 director and which of them is a 3 director. This the reason why he told you to draw the structure. Examiner uh, ask you to draw the structure is whether the examiner wanted to see whether you are familiar with the 2,4 director concept, directive concept or not. So this CH3 methyl group is a 2,4 director. Why? Because there are single bonds in this CH3, and this benzoic acid is a 3 director, because there is a double bond in this carboxyl group. Okay, so one with the double bond is a 3,4 director. Okay, so you will count the position from this methyl carbon. Okay, so 1 2. So you can attach this nitro group over here, or you can attach it on 4th position, or you can attach it on 6th position. Okay, so that's correct. And this benzoic acid, on this benzoic acid, it will attach on 5 or 3 position. So 1 2 3. So it will attach over here. Okay, so that's how you will draw these structures. Now part C, a reaction scheme is shown in figure 7.2. Describe the reagents and conditions to produce this compound from this compound in the reaction 2. Okay, so this is actually a amine. Amine is changed into this, you can say this is an diazonamine. Okay, so what are the reagents to change amine into diazonamine? So it's actually the reagent is actually HNO2. Okay, it's nitrous acid, and these conditions are actually the conditions are actually temperature between temperature between 0 degree and 10 degrees Celsius. This mixture, this reaction occurs below 10 degrees Celsius. This is the condition you have to remember to form the diazonamine. And you can also write on the reagents NaNO2 plus HCl, because these sodium nitrous, this reacts with HCl to form HNO2. Okay, this HNO2 is very unstable, but so you can write these two reagents as well. Okay, or you can also write this HNO2. So now part 2, describe how this CH3 C6H4OH can be produced from this diazonium ion in reaction 3. So this is actually a phenol. So phenol is produced from diazonium ion by reacting it with steam or water, you can say, and the temperature above the 10 degrees Celsius. Okay, so temperature about 10 degrees Celsius and water. Okay, now draw the structure of the di molecule Y formed when this diazonamine and this phenol react together in reaction 4. Describe the conditions for this reaction. So conditions for these reactions are actually uh, temperature below 10 degrees Celsius, temperature below 10 degrees Celsius, and it's a NaOH, aqueous NaOH. Okay, because phenol is not strong enough to react with diazonium ion. So when it reacts with NaOH, so it forms this ion. Okay, so this reacts with actually this reacts with diazonium ion to form this di Y. So what will be the structure of di Y? So it's going to be firstly we will have this group. So CH3 C6H4, and then you have this di group. Okay, and then you have C6H3 H3 sorry H3 and CH3OH. Okay, so this is your structure. How I've drawn this structure, let's draw. This is a benzene ring, and you have this azo group. Okay, here you have a methyl group, and this azo group reacts with other benzene ring um, like this. This is your methyl group, and this is your OH group. Okay, so if you see the number of carbons and number of hydrogen, so this will be your structure. Okay, now moving towards question number 8. Okay, okay, so question number 8. When answering this question, it should be assumed that altogether hydrogen atoms in benzene ring result in a single unsplit peak at this range, this the proton NMR spectrum. Okay, at a chemical shift of 7.2. The structure of 5 isomeric ketones PQR and RS and T are given. Okay, identify all the chiral carbons on the structures above. Label each chiral carbon with an asterisk. Okay, so let's first draw their displayed formula. Okay, uh, So its P is L. Okay, let's make this correctly. So P, this is the structure of P. So CH and CH3. Okay, then you have Q, you have this carbon double bond, and then you have CH3. Okay, then you have R, which is CH3, CH2, then carbonyl ketone group, then CH2, and then you have CH3, and then you have S. This is the S, CH2, CH2, then you have ketone, and then T. Then you have T, CH, CH3. Then you have this ketone group. Then you have CH3. So these are your structures of these P, Q, R, and R, S, and T. Okay. Identify all the chiral carbons. So you have to find all the chiral carbons. These carbons. Okay. So let's find out the chiral carbons. In P, you won't see any chiral carbon because there is no such carbon which is attached to 4 different groups. And actually, there is only in T there is a chiral carbon. So you can see here. This is a chiral carbon. Okay. So you have to mark a steric on this carbon. Okay. So this is your P. This is on. This is your chiral carbon. Okay. Now part B, the proton NMR spectrum of one of the 5 isomeric isomers P, Q, R, S, and or T is shown in figure 8.1. Okay. Identify which of the compound P, Q, R, S, or T gives this spectrum. Draw the displayed formula of the compound you have identified. Identify the protons responsible for the peaks at the chemical shift of 3.7, 2.5, and 1 on the structure you have drawn. Okay. So let's so you have this is peak due to benzene ring. Okay, I told you that the you have to assume that the altogether hydrogen atoms in benzene ring give a result of unsplit peak at 7.2. Okay, so we will ignore this peak for the while because uh, there is a benzene in all of these compounds. Okay, so this peak will be in all of these compounds. So let's forget this peak for a while. Now let's see the P. So in P, if you see this carbon, uh, this carbon, this hydrogen, sorry. So this hydrogen, the carbon which is attached to this hydrogen has the 6 hydrogens on the remaining. So it should give multiplet because, but there is no multiplet, so it won't be P. Okay. Now let's see Q. So in Q, you have for this, due to these hydrogens, you must have a triplet. So you have a triplet because there is a there are 2 hydrogens on the adjacent carbon. Okay, so there is a triplet. Okay, now you also must have a quartet due to these hydrogens because there is a, okay, you must have a multiplet. Okay, but there is no multiplet over here, so this won't be Q. Now CR, you must have singlet, because due to these hydrogens, because there is no uh, hydrogen on the adjacent carbon. Okay, so singlet. Yeah, so you have a singlet. Then you have these, due to these hydrogens, you must have a quartet. So you have a quartet, and due to these hydrogens, you must have a triplet. So you have a triplet. So these all three peaks are in this compound. So it must be the NMR spectrum of R. So let's draw the structure of R. We have already drawn. It's a split formula. So let's draw this. Draw the displayed formula. Okay. So you have a benzene ring. Then you have CH3, CH2, sorry, CH2. Then you have a carbonyl group, and then you have CH3, CH2. Okay, so this is the structure of R. Okay, now name the. You have to identify the protons responsible for the peaks at uh, these chemical shift 3.7, 2.5, and 1. Okay, so at 1 you have a tripleted one. So which hydrogens are responsible for this triplet? These are these hydrogens. Okay, so on the structure, you have to find out which of these. So let's make this. So this is R, and for 1. Okay, so for the chemical shift of 1, this C6H5, and then you have CH2, then you have COCH2, CH3. So these hydrogens are responsible for this peak triplet. Okay, triplet, due to this triplet at chemical shift of 1. Then you have 2.5. So let's first draw the 6 C6H5 H2 CO C2 H3, then 3.7 6 H5 CH2 CO CH2 CH3. So you have quartet at 2.5, and the quartet is due to these these hydrogens. Okay, then you have a singlet, and this singlet is due to this hydrogens. Okay, so now you have identified all of these hydrogens which are responsible for these peaks. Okay, now moving towards next part, name the splitting pattern of the peak at 3.7. 3.7. So it's a singlet. Explain why it has this splitting pattern, because there is no hydrogen on the adjacent carbon. So it's a singlet. Okay, and because there is no hydrogen on neighboring carbon. Okay, okay. Now moving towards part C. Choose from the letters P, Q, R, S, and T to identify the two compounds that each have a doublet peak in the proton NMR spectrum. Doublet. Okay. So let's see which of these compounds will give a doublet. So let's first see P. So you have this. So if you see this carbon, these hydrogens are attached to this. Uh, let's draw these structures again, because there is, you won't understand this anymore. Let's delete all this. So let's draw these structures again. So you have a benzene ring, then you have carbonyl group, then you have CH3 and CH3. Then you have benzene ring for Q, you have a ketone group, CH2, CH2 and CH3. Then you have this group CH2, C double bond O, CH2, CH3. So if you see these hydrogens, these both hydrogens are attached to the neighboring carbon has only one hydrogen. So these both will give a doublet. So P will give a doublet. Okay. So P will give a doublet. Two compounds. You have to find two compounds. So P will give a doublet. Now the second compound. So if you see in the Q won't give a doublet, nor will R give a doublet, because there is no carbon which has a single hydrogen. But if you see this T, so these hydrogens have these are attached to the carbon which has a single hydrogen. So this will also give a doublet. So P and T. Okay. Now the compound with only 3 peaks in its NMR spectrum. So it's going to be let's see, it's going to be P, because these both hydrogens have same environment. Let's draw this environment again. CH3. So these both hydrogens have same environment. Then you have this hydrogen, this has a different environment. Then you have these hydrogens. So 3 peaks. Okay. So only 3 peaks will be given by P. But in the others, Q, you can see this hydrogen has a different environment. This hydrogen is also a different environment, and these hydrogens have different environment, and the ring will have a different environment as well. Okay, the ring will have a different environment. So there will be 4 peaks in R. So and there will be 4 peaks in Q and R, and but so only there will be P which has three 3 peaks, which will show 3 peaks. P. Now suggest a suitable solvent that should be used for obtaining the spectrum shown in figure 8.1. So the solvent which we use is CdCl3. Okay. Now part E, you have to remember this solvent which we use, CdCl3. Okay. The proton NMR spectrum of compound T is compared with, in the presence of D2O. It is a heavy water, and in the absence of D2O. Okay. Describe any difference between the two spectra. Explain your answer. So there in T, actually this D2O is used to find out the OH group and NH group, but there are no OH groups or NH groups in these compounds. You can see there is no NH or OH group. So there will be no difference in these both spectra, whether the T is compared in presence of D2 or in the absence of D2, because there is no OH or NH group. D2 actually disappears the peaks of OH and NH. Okay, but there are no OH or NH groups, so D2O will have no effect, so no difference. So there will be no difference. So no difference, because no protons or H plus ions that exchange with D. Okay, D is actually a deuterium. Okay, now F. Complete the table 8.1 below to give the number of peaks in the carbon 13 NMR spectrum of each of the compounds. So for the carbon 13, okay, So let's firstly find the environments of each carbon. Let's start from the ring. So this carbon will have a different environment. Then you have these two carbons, they will have a same environment. Then these two carbons, they will also have a same environment. And then so this carbon, this will have also a different environment. 1 2 3 4, and these both carbons will also have a different environment, so there will be a 6 peaks. Okay, there will be 6 peaks of this compound. Then you have this carbon, so these both will have a same environment, and these both carbons will also have a same environment. These two will have a same environment, and these two will also have a same environment. Okay, so 1 2 3 4, 4 peaks. Now 5, oh sorry, this compound. So this carbon and this carbon, they will have a same environment. Okay, and this carbon and this carbon, they will have a same environment. Two environments. Then you have 3 4 4 and 5. Okay, so five peaks will be shown. Now for this compound, so in this compound, these both carbons will have a same environment. Actually these four will have a same environment. Okay, then you have these two carbons, these two carbons will have a same environment. Okay, and then you have these two carbons, they will have a same environment, so only 3 peaks will be shown. Okay, now moving towards question number 9. Tyrosine and lysine, shown in figure 9.1, are naturally occurring amino acids found in proteins. Okay, the isoelectric point of lysine is 9.47. Draw the structure of lysine at the stated pH in the boxes given. Okay, so at pH 7, there will be more H plus ions, so it will form a carboxylic acid. So this is lysine. At pH of an isoelectric point, this lysine will be in the ether form. Okay, 1 2 3 4 5. So this will be in this form. Oh, so this lysine will be in this form, NH3 plus. Okay, this will have a, this will be in Zoeter form at pH of 9.47 at its isoelectric point. Okay, so and then at a pH of 7, let's draw this structure at pH of 7. So at pH of 7, you will have let okay, so let's draw it. NH2, then you have this carboxylic acid, so it will be a carboxylic acid over here. Then you have this H plus. Okay, and then at last the pH at 12, or negative, and then you will have a amine group. So these are your structures at pH of 7, 9.47 and 12. Okay, now part B. When ethanoic acid is treated with PCl5, product D is formed. When D is added to tyrosine, two different isomeric products E and F are formed. Okay, so E has an ester linkage, F does not have. So draw the structures of D, E, and F. So when this ethanoic acid is reacted with PCl5, D is formed, so it must be in ethanoyl chloride. So the structure of ethanoyl chloride is CH3 COCl. Okay, so this is the structure of ethanoyl chloride, and when this D is reacted with tyrosine, this is your tyrosine, so it will this Cl group, this ethanol chloride will react with this OH group and NH group. So in the first, so E must be, so it says E has an ester linkage, so it must have reacted with OH, and F does not have an ester linkage. So in F, this amide linkage would have formed. So let's draw the structures. So you will have 1, 2. Okay, so these will be your structures. Okay, so this is your structure for this E. There is an ester linkage, and for F, there will be no ester linkage. So it must be like this. Um, like this. Okay, like this. So these are your structures for E and F. Okay. Now moving towards next part. Part C. Complete table 9.1. By drawing the structures of the organic product formed when the tyrosine reacts with each of the named reagents. Okay. Ignore the directing effect of this substituent. Okay. Okay. So when tyrosine reacts with an excess of Br, so this Br will be attached in the 2, 4, and 6 positions, but you can see at 4 position you have this compound attached, so 2 and 4, 6 position. So this compound and this tyrosine OH, then you have Br, then you have another Br group, then you have this group. This is your structure when it reacts with an excess of uh, Br, bromine. Okay, and when an excess of NaOH, it reacts with an excess of NaOH. So this NaOH will react with this carboxylic acid. Okay, so it will also react with phenol, because NaOH can react with phenol. So it will form ONa. Then you have this ONa and amine. Okay. Now, when it reacts with an excess of nitric acid, so when an excess of nitric acid is reacted, the nitro group will be attached at 2, 4, and 6 positions, but 4 position is already occupied. So nitro group at 2 and 6 position. Okay. So these are your structures. Now moving towards next part, part D. A mixture of tyrosine and lysine can be separated by a thin layer chromatography. Under certain conditions, the RF value of lysine is 0.4, 0.14, and the RF value of tyrosine is 0.45. Okay, what is meant by the RF value? So it is actually the distance traveled by amino acid divided by, so distance traveled by amino acid divided by distance traveled by solvent. Okay, distance traveled by solvent. It's actually the formula for the RF value. Okay, so just an explanation for the distance difference in the RF values. So lysine has a smaller RF value than of tyrosine, so it means this tyrosine must be more soluble in this solvent. Okay, or you can also say that this lysine is more attracted to the stationary phase. Okay, so let's say tyrosine is more soluble in the solvent. Okay, in the solvent used, or you can say this lysine is less soluble. The one which is more soluble will uh, travel further. Okay, so tyrosine must have traveled further, so it means it is more soluble. Or you can also say that this lysine is more attracted to the stationary phase. So that's all for the day. Your paper is finished. This 9701 of 1 October November 2022. I hope you like the video, and if you haven't subscribed my YouTube channel, do subscribe for the more papers. Thanks for watching and take care.